Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome, you curious learner, to a breakdown of some truly cutting-edge science.
It really is.
Our mission today is complex, but I think incredibly thrilling. We're diving into the decades-long mystery of dark matter.
The big one.
The big one. And we're using cosmic cannonball stars traveling at speeds that just defy galactic gravity to solve it.
Right.
This isn't just theory. This is like astronomical cartography, using extreme speed to map the invisible.
That's a perfect way to frame it. We're looking at some groundbreaking research that focuses on tracing these stellar high-speed offenders, these runaway stars.
Runaway stars, I love that term.
And we're using them to map the gravitational landscape of the Milky Way with just unprecedented precision.
So the core idea is that their paths, their trajectories, reveal the unseen mass.
Exactly. The specific measurable trajectories of these extremely fast stars reveal all that unseen stuff, including the elusive dark matter that dictates the galaxy's entire dynamic structure.
Especially way out in the galactic halo, right?
Especially far out in the immense galactic halo, yes.
So the material we're drawing from today comes from a detailed article. It outlines a very specific, very rigorous search for these stars.
Conducted by Chinese astronomers, published in the Astrophysical Journal. A fantastic paper.
It really is. And what I love about this research is its intellectual elegance. It shows how astronomers leverage an old, an established, reliable, stellar phenomenon.
Something we understand really well.
Exactly. In this case, pulsing stars that act like perfect cosmic clocks. And they use that to tackle one of modern physics' deepest and most persistent mysteries. We're using a predictable ruler to measure the extreme, chaotic edges of our own existence.
That's it. What we're looking for is precisely how these stellar objects, known as hypervelocity stars, act as test particles. They're the perfect tracers.
Tracers of what, exactly?
Of the Milky Way's gravitational potential, particularly in those outer, dark matter-dominated regions of the galactic halo. So we need to unpack why this specific stable type of variable star was chosen for this role, and what their final distribution, where they are in the sky, where they came from, tells us about the structure of the dark matter that we literally cannot see.
Okay, let's unpack this. Before we get to the data crunch, let's get a clear, visceral picture of what exactly these incredible speed demons are.
Good idea.
Because calling them runaway stars, that feels like a significant understatement. They are actively leaving.
Oh, absolutely. It's crucial to understand the scale of their defiance. These are not merely stars orbiting a little faster than average.
Wow.
These are objects possessing enough kinetic energy to completely overcome the collective gravitational pull of hundreds of billions of stars, the gas, the dust, and all the dark matter that makes up the entire Milky Way galaxy.
Wow.
They are, for all intents and purposes, space projectiles.
Hypervelocity stars, or HVSs.
Yeah?
It certainly sounds like something ripped straight out of science fiction. An interstellar bullet.
It does, doesn't it?
But the concept is actually, quite old. The source material notes that they've been important since the 1920s for studying the dynamics of the Milky Way.
That's right. That historical continuity is fascinating. It offered an early, an indirect window into its mass structure before we even had the precise technology we have today.
So what's the definition? What makes a star hypervelocity?
Fundamentally, HVSs are defined by their extreme speeds. The general threshold is a tangential speed of 1,000 kilometers per second.
1,000 meters per second.
Per second or more. And that speed isn't just fast. That speed is the critical determinant that deems them gravitationally unbound from the Milky Way.
Unbound?
Entirely. They are on a one-way, non-repeating trajectory out into the intergalactic void.
1,000 kilometers per second. Just to give you some context, if you could drive that fast, you would cross the entire continent of Australia in about 8 seconds.
That's a great way to put it. It's an insane speed on a galactic scale.
So if they're leaving, why are they so useful? Why do we care about their flight path?
Well, the utility is profound because they are literally mapping the galaxy's gravitational fingerprint.
Okay.
Imagine dropping thousands of marbles onto a complex, invisible terrain. By reconstructing and carefully tracing the trajectories of these runaway stars where they came from, the precise arc they're following, scientists can effectively map the gravitational potential of the Milky Way.
So you're watching the marble roll to figure out the shape of the ground.
Exactly. This gravitational map shows us exactly how masses interact within the galaxy, and crucially, it allows us to infer the detailed distribution of dark matter in the galactic halo.
They're test particles for gravity itself.
Precisely, probing the deepest parts of our galaxy's structure.
And the halo is the ultimate target area for the search, right? Because that's where most of the invisible mass is supposed to be.
That's exactly right. The halo is this huge, roughly spherical volume that surrounds the much flatter, visible stellar disk of the Milky Way.
Where we live.
Where we live, yes. While the disk contains virtually all the stars we can see, most of the total mass of the galaxy, somewhere around 90% of it, is believed to reside in that massive, invisible halo.
Mostly in the form of dark matter.
Primarily in the form of dark matter. So if a star is moving through the halo, its trajectory is dictated almost entirely by that unseen mass.
So we don't need to see the dark matter.
We don't. We just need to see how the visible star responds to its gravitational influence.
The source material gives a really great concrete visualization of how this tracking actually happens. It mentions the positions and trajectories of around 20 HVSs have already been reconstructed.
Right, using existing data.
From the European Space Agency's Gaia satellite, which has been up there since 2013.
And Gaia is truly an astrometry powerhouse. It's indispensable, really.
Indispensable how?
Well, without that kind of positional accuracy, this research wouldn't be possible. It provides the extremely precise positional data and proper motion.
Proper motion being the movement across the sky.
The movement across the sky, exactly. That's what you need to backtrack these stars to their point of origin.
So you combine the position with velocity measurements.
Right. You combine that high-precision positional data with separate spectroscopic velocity measurements, and you can construct a highly accurate three-dimensional model of the star's movement.
And that gives you the galaxy's gravitational influence.
It does. 20 HVSs gave astronomers a proof of concept, a sort of first look. But the new research we're discussing today aims to increase that number dramatically.
Because more data points mean a better map.
A much better resolution for the dark matter map. It allows us to distinguish between, say, a smooth, uniform dark matter halo and a clumpy one, which is a huge question in cosmology.
To truly appreciate how extraordinary the speed of an HVS is, we really need to spend a moment on the concept they're defying. Escape velocity.
Yes.
Because they aren't just running away from the Milky Way. They have enough velocity to just coast away from it forever.
That's the critical distinction. They aren't just completing a very wide orbit. They possess enough kinetic energy to completely overcome the gravitational energy binding them to the galaxy.
So let's ground ourselves with a basic definition here. What exactly is escape velocity?
Escape velocity is the minimum speed required for an object to completely coast out of a gravitational well.
A gravitational well being, like a planet or a star.
Any massless body. It's the speed needed to reach an infinite distance away without any further propulsive energy. It's the minimum launch speed you need to kiss a celestial body goodbye forever.
And when you start comparing this across different celestial bodies, you really begin to grasp the sheer scale of the forces holding our galaxy together.
Exactly. Let's start small, or, relatively small. Earth's escape velocity, which we're familiar with from launching rockets, is 11.2 kilometers per second.
Okay, 11.2 kilometers.
If you could somehow toss a satellite at that speed straight up, it would just coast out into solar orbit and never return to Earth.
Now, step it up to the sun, which dominates the solar system's gravity.
The sun's gravity well is staggering. Its escape velocity at its surface is 618 kilometers per second.
Wow.
If you were standing on the sun, hypothetically, of course,
right,
you'd need to launch at over 600 kilometers to leave. But gravity weakens with distance.
The inverse square law again.
Exactly. So the escape velocity required from Earth's orbital position, which is about 150 million kilometers away, to leave the sun's gravitational grasp is much lower.
But still immense, I'm guessing.
Oh, yes. It's still 42 kilometers per second.
So even that, 42 kilometers, is nearly 4 times faster than what's needed to leave Earth.
It is.
The source material gives a couple of truly extreme analogies to illustrate the kind of power you need to achieve these speeds.
There are wonderful illustrations of extreme physics. Think about rocks ejected from Earth by asteroid collisions.
So like the Martian meteorites they find in Antarctica.
Exactly those. A massive impact is capable of imparting enough energy to literally blast material off a planet's surface and send it into interplanetary space. It achieves or exceeds the local escape velocity through sheer kinetic force.
But the most famous one, almost mythological, and this is a favorite of mine just based on the sheer absurdity of it, is the theoretical steel lid.
Yes, the famous cosmic cannonball, but man-made and atomic-powered.
Right.
This refers to the theoretical fate of a steel cap covering a blast hole from a 1957 underground nuclear test in Nevada. Operation Plumb Bob.
Plumb Bob.
Calculations based on the immense energy release suggested that this cap could have been violently ejected by the expanding gases and shockwave at an estimated 6 times Earth's escape velocity.
So 6 times. That's over 67 kilometers per second.
It is.
That's faster than the sun's escape velocity from Earth's orbit.
Exactly. Now, in all likelihood, the cap almost certainly vaporized completely from the heat and the shockwave.
Right. It didn't actually fly into space.
Probably not. But the theoretical energy imparted in that instant is immense. It represents a force almost impossible to imagine in normal life. And that really sets the stage for what we're discussing with HVSs.
And here is where it gets really interesting, as we move from planetary and solar scale to the galactic scale.
The big jump.
The escape velocity from the sun's position within the Milky Way, meaning overcoming the gravity of all the stars, gas, and critically all the dark matter of the entire galaxy, is estimated to be about 550 kilometers per second.
And this is the magic threshold.
Because an HVS travels at 1,000 kilometers per second or more.
Nearly twice the minimum velocity needed to leave the galaxy entirely. They are truly, truly gravitationally unbound, on a straight shot into the void of intergalactic space.
Which means whatever launched them had to provide a phenomenal energy boost, something that could overcome the force field of the entire galaxy's mass, most of which is dark matter. So if the standard engines of stellar life fusion, gravity, typical orbital mechanics can't do this, what incredible engine launches these stars to such extreme velocities? It requires something extremely powerful.
That's the mystery. And fortunately, we have a very strong, well-established hypothesis, backed by observational evidence, which connects these stellar speed demons directly to the single most massive concentrated object in our galaxy.
Sagittarius A star.
The supermassive black hole at the very heart of the Milky Way.
So the most prominent method for creating these HVSs is a gravitational slingshot with SGR A star.
That's the most prominent and widely accepted method, yes.
It's a remarkable piece of galactic engineering to think about. A black hole acting like a stellar catapult. This mechanism has a specific name, right?
It does. It's called the Hills mechanism.
The Hills mechanism.
That's right. It was first proposed by astronomer Jack Hills way back in 1988.
1988. That's incredible. That's well before we had definitive proof that SGR A star was a supermassive black hole.
It is. It was well before we could track stars with the precision we have today. The theory describes a very specific 3-body interaction that only a supermassive black hole could facilitate because of its extreme gravitational field and density.
Can you walk us through the mechanics? What actually happens during a Hills interaction? How does a black hole fling one star away but keep the other?
Okay, so it requires a star system that's already quite common. A binary star system.
2 stars orbiting each other.
Right, orbiting a common center of mass relatively close to one another. Now, this binary system has to venture too close to the event horizon, or at least the very strong gravitational domain of SGR A star.
Okay, so they wander into the danger zone.
They do. And as they pass, the black hole's immense tidal forces dominate the interaction. They essentially tear the binary system apart.
And what happens then is a transfer of energy and momentum.
Exactly. One star of the binary pair is captured into a tight, close, fast-paced orbit around the supermassive black hole. Or sometimes it spirals down and is consumed entirely.
And the other star, the companion.
That's the critical part for our discussion. The gravitational interaction essentially steals the orbital energy from the captured star and transfers it into kinetic energy for the companion star. And it simultaneously flings that companion star away from the black hole at an extremely high velocity.
It's like a gravitational whip.
A perfect analogy, achieving speeds far beyond what a simple planetary slingshot, like with our space probes, could ever manage.
And the existence of these stars tracing back to the galactic center is proof in itself.
Absolutely.
You see the star coming out, something incredibly massive and dense had to put it there.
Right.
The HVSs are the product, but they're also observational proof of the black hole's mass and its dynamical environment.
Completely. They confirm the black hole isn't just a static object, it's dynamically active. It's frequently interacting with nearby stars, particularly those in dense binary systems. The speed distribution of these escaping stars can even tell us about the mass of SGR-A star.
How so?
Well, the more massive the black hole, the faster the ejection velocity it can produce.
To really drive home the magnitude of the speed, the source highlights a striking example. A star jettisoned via this Hill's mechanism was observed in 2019, traveling at an astonishing 1,755 kilometers per second.
That is nearly 2,000 kilometers per second. It's just staggering.
That star is traveling at 0.6% the speed of light.
An immense speed. And it's a measurable, definitive speed. It's not an estimate. It's derived from combining precise distance and velocity data.
And crucially, that speed is vastly greater than the 550 kilometers escape velocity of the galactic center.
Which confirmed beyond any doubt that the star was gravitationally unbound. It was a real-world, observed validation of the 1988 Hill's mechanism theory.
So we know the HVSs we're looking for are legitimate probes of the galaxy's mass structure because we know how they're manufactured.
Right. And this knowledge acts as the motivation for the new research. Astronomers are highly motivated to find many, many more of these stars because each one is an individual data point in our gravitational map.
But there's a major challenge.
A huge one. You can't map a trajectory without a ruler. The key difficulty, as this new research shows, lies in knowing precisely, to the millimeter, in astronomical terms, how far away these stars are.
Because if the distance is wrong, the tangential velocity is wrong.
And the entire gravitational map is corrupted, it all falls apart.
And that's where the unique methodology of this Chinese research team comes in, bringing us to a special class of cosmic clocks.
Exactly.
So finding HVSs is difficult. They're rare, they're often dim, and their speed makes them hard to measure.
It's a real challenge, which is why this new research, led by Haozu Fu of Peking University, decided to flip the script.
How so?
Instead of looking for just any fast star, they looked for a specific type of star they knew they could measure perfectly.
To get back to targeted, large-volume search.
Exactly.
And that star is the RR Lyrae star, or RRL.
The RRL.
These are maybe less famous than the brighter Cepheid variables that Edwin Hubble used, but they're just as vital, especially for mapping the older, fainter parts of the galaxy.
RRLs are an absolute gift to astronomy. They're old, giant stars that pulse. They expand and contract with a very regular rhythm.
And they're found in the right places.
They are. They're abundant and commonly found throughout the thick disk and, critically, the halo of the Milky Way. They often reside in ancient globular clusters.
The Milky Way has, what, over 150 of those?
Over 150, yes. These dense, spherical collections of ancient stars, many of which populate the halo.
So they're ancient, they're widely distributed in the target region, the halo, and most importantly, they have this distinct, regular, predictable pulsation.
That's the key. Their periods are quite short, ranging from 0.2 to about 1 day. That regularity, that predictability, is what makes them such a perfect ruler.
The predictable pulsation makes them incredibly useful as highly accurate distance indicators. The classic standard candle.
The classic standard candle. Think of it like a light bulb where you know the exact wattage it was manufactured with.
Right.
If you know the total energy output, the intrinsic luminosity of the object, and you measure how dim it appears from Earth, you can precisely calculate the distance using that fading relationship.
But how do they determine that intrinsic luminosity so precisely for an RR Lyrae star? It's not like they come with a spec sheet.
They don't, but their physics are highly regulated. Their intrinsic luminosity is relatively well determined from a specific empirical relationship that connects 3 measurable properties.
Okay, what are they?
Their pulsing period, their absolute magnitude, and their metallicity. This is where the reliability comes in.
Let's pause on metallicity. That sounds technical, but it seems crucial. What does metallicity mean for a star like this?
Right. So astronomers, in their usual fashion, simplify things greatly. To us, metals are any elements heavier than hydrogen and helium.
Everything else is a metal.
Everything else is a metal. RRLs are very old stars, often called population 2 stars, meaning they formed early in the universe. Yeah. They tend to be metal poor compared to newer stars like our sun.
And that affects their brightness.
It does. This metallicity, the percentage of heavy elements, affects how light is produced and absorbed within the star, which in turn influences its intrinsic luminosity.
Okay, so you have to account for it.
You have to. You can think of metallicity like a necessary correction factor. Imagine RRLs are standardized light bulbs. Older generations, the metal poor ones, were made with slightly different filament material, their metallicity. That makes them intrinsically a bit brighter or dimmer than newer ones.
You have to know the filament type to apply the correction.
Exactly. Before you can use the light bulb as a perfect distance ruler, the relationship derived from stellar physics lets us know the absolute magnitude, the total intrinsic energy output once we measure the star's period and its metal content via spectroscopy.
And that brings us to the final calculation step, the inverse square law.
That's it. Knowing their absolute energy output, their true intrinsic brightness, and then precisely measuring the energy we get here at Earth, their apparent brightness, lets astronomers calculate their exact distance.
And this precision is not optional.
It is vital for trajectory tracing. If your distance measurement is off by even a small percentage, your velocity calculation and trajectory trace will become useless when you're trying to determine if a star has actually escaped the galaxy.
So the RRLs provide the reliable, pre-calibrated ruler you need for this search.
Exactly.
So, armed with this reliable ruler, the research team could begin their massive data hunt, looking for RRLs that just happened to be moving fast enough to be HVSs.
It was a true needle-in-a-haystack problem, but they had the right tool.
So the initial phase was pure data mining.
Pure data mining. The researchers started their quest by beginning with 2 large published star catalogs. And we need to appreciate the sheer scale of this initial data set.
They started enormous. One catalog had, 8,172 RRLs from the Sloan Digital Sky Survey. And they combined this with an extended catalog that had a staggering 135,873 RRLs.
All of which had distance and metallicity estimates derived from Gaia photometry.
So they started with well over 140,000 potential targets. That's a huge number.
It is. But as you said, the real science starts with the filtering. You can't analyze 140,000 stars in the detail required. So what was the critical filtering process they used?
Well, the data set had to be filtered drastically. They weren't just looking for any RL, they were looking for the ones with the highest quality data.
Right. The data had to be good enough to confirm the extreme speed.
So the critical step involved prioritizing the quality of the velocity data over everything else.
And this is where we have to distinguish between the 2 components of stellar motion. You need 2 primary measurements to calculate the star's total 3-dimensional space velocity.
And that's the speed you compare to the 550 kilometers escape velocity.
Exactly. So what are those 2 components?
Okay, so first you need the tangential velocity.
Right. The movement of the star across the sky perpendicular to our line of sight. Gaia is excellent at measuring that.
And second, you need the radial velocity.
Critically, yes. The star's movement directly toward or away from us along our line of sight, and that's measured using the Doppler shift of the light from the star.
And the crucial criterion for the team was eliminating almost all the stars that didn't have spectroscopic measurements that provided those radial velocities with sufficiently low uncertainties.
Sufficiently low uncertainties. That was the key. If the radial velocity measurement, the movement along our line of sight, is fuzzy or uncertain, the resulting calculation of the full 3D space velocity becomes, useless.
Hold on. If they have an accurate distance from the RRL property and the tangential movement from Gaia, why does uncertainty in the radial component kill the whole calculation?
It's a problem of error propagation. Imagine you're firing a cannonball into space and trying to prove it reached 1,000 kilometers.
Okay.
If you're certain about the direction, the tangential component, but you're uncertain about the thrust, the radial component, you can't be sure of the final speed vector. The total space velocity is the vector sum of those 2 components. If one component is highly uncertain, the error margin on the final space velocity just balloons. You can no longer definitively state that the star is moving at 1,000 kilometers and not, say, 450 kilometers.
So they had to be ruthless.
They had to be ruthless in discarding low-quality velocity data. Precision is far more important than quantity for mapping dark matter.
And the numbers bear that out. The source notes that this detailed filtering process reduced the relevant data set drastically, down to just 165 hypervelocity RRL candidates.
From over 140,000.
That's an enormous, nearly 1,000-fold reduction.
It illustrates the extreme rigor of modern astronomical searches. You need the quantity to start, but ultimately you rely entirely on the quality of the velocity readings.
And those 165 were just candidates. They did a final vetting process.
They did.
What did that final validation entail?
The group then meticulously examined each star's light curve, the precise measurement of its pulsation profile over time, to select the best and most consistent Doppler shifts for the remaining stars.
So they were cleaning up any potential noise in the data?
Essentially, yes.
Yeah.
This final, highly detailed check yielded 87 reliable hypervelocity RRL candidates. These 87 stars were the payoff.
And within that group, there was an even smaller subset of truly extreme speed demons.
Yes, a powerful indicator of the strength of the ejection mechanism. A subset of these 87 stars, 7 of them, specifically, had a confirmed tangential velocity above 800 kilometers per second.
So if you combine that with the radial velocity, these are definitively unbound.
They are truly on their way out of the Milky Way. They've won the gravitational fight.
So once they had these 87 reliable stars, the team analyzed their locations and concentrations. And this is where the results start painting a picture of where they came from.
And by extension, the gravitational map of the galaxy. The distribution of those 87 stars immediately suggested 2 distinct groups. This is arguably the first major discovery of the research.
What were the 2 groups?
One group was concentrated towards the Milky Way's galactic center,
Which strongly, overwhelmingly, points toward the Hill's mechanism involving SGRA star.
Yes, that's the expected result, the classic HVS population.
Wow.
But the second group was localized around the large and small Magellanic Clouds.
Our 2 biggest satellite galaxies.
2 irregular dwarf galaxies relatively close to the Milky Way, currently in orbit around us. And this grouping is immensely interesting. It points to potential ejection mechanisms outside of our own massive galactic core.
So something massive in or near the clouds is launching these stars.
That's what it suggests.
The clustering of these stars immediately suggests something fundamental about their ejection mechanisms, linking back to that slingshot idea, but now, potentially, on a different scale.
Right.
So if those gravitational fingerprints are pointing to 2 very different launch pads, SGRA star and the Magellanic Clouds, what does that variance tell us about the massive invisible structure those stars are now flying through?
This transition leads us right into the profound implications of this discovery for the dark matter search. We now have a list of well-measured targets whose origins are clearly defined and whose paths tell us about the mass they've encountered.
So let's talk big picture. What does this all mean for the deepest mystery in modern physics? The grouping of these stars near the center or near the Magellanic Clouds suggests they reached hypervelocity through the Hills or a similar mechanism.
Right, being flung away from their host systems, whether that's the Milky Way center or the core of the clouds. And that finding confirms key assumptions about galactic dynamics.
It validates the theories.
The presence of these stars, many with movements confirmed to be exceeding the Milky Way's escape velocity, it validates the theories about extreme gravitational interactions. These HVSs are the physical manifestation of violent galactic-scale physics.
But how do these individual stellar paths translate into a map of the invisible dark matter? I think that's the hardest concept to grasp.
Think of it like a probe. Identifying these runaway stars allows the properties of the Milky Way halo to be studied further, far beyond the visual reach of the disk where most of them live out their journey.
But their movement acts like a navigational tool.
It does, revealing where the largest gravitational influences are located. For example, if the path of a hypervelocity star is perfectly straight, it suggests the dark matter halo it's moving through is smooth and uniformly distributed.
But if it wobbles?
But if the star's trajectory shows subtle wobbles or changes, it implies the star is encountering dense clumps or subhalos of dark matter.
And these clumps are predicted by cosmological models, right?
They are, but they're incredibly difficult to detect directly. HVSs essentially provide the first direct proof of the clumpiness of the dark matter distribution in the halo.
So their movements are charting the terrain of the dark matter landscape. If they unexpectedly slow down in a certain region, it means that region is gravitationally heavier than we thought, suggesting a high concentration of dark matter there.
Precisely. They are taking the measure of the dark matter landscape for us. Because dark matter dominates the halo's mass, it makes up the vast majority of the invisible mass that surrounds us. Mapping the gravitational potential based on these stellar trajectories is essentially mapping the structure, distribution, and clumpiness of the dark matter.
And the RRL HVSs give us an excellent sample size to do this.
And reliable data points to conduct this detailed cartography.
And then we get to that second population, the truly fascinating outlier group, the stars around the Magellanic Clouds. If these dwarf galaxies are ejecting HVSs, that has major implications.
This is perhaps the most exciting finding. A star must be ejected at speeds nearing 1,000 kilometers to be registered as an HDS.
Right.
To provide that kind of slingshot, the object doing the flinging, whether it's a central black hole or some other massive dynamic, must be interacting with an extremely deep gravitational well.
So for the Magellanic Clouds, which are dwarf galaxies, to generate such high-velocity stars,
It means they must have far more mass, and thus far more dark matter, than their visible stellar population would suggest.
So the finding isn't just mapping the Milky Way's dark matter. It's using HVSs as a litmus test for the mass of our galactic neighbors.
That's a great way to put it. The fact that the clouds appear to have powerful enough gravitational machinery to launch HVSs at us implies that their surrounding dark matter halos are much deeper, much more massive, and perhaps structurally different than current estimates suggest.
And that would change a lot.
It's a critical inference.
Yeah.
The current understanding of how the clouds interact with the Milky Way and how the Milky Way is slowly consuming them is based largely on models of their estimated mass.
So if this HVS grouping confirms that the clouds are far heavier than we assumed,
Then those galactic interaction models need massive revision. It suggests the influence of the clouds on our own galaxy's structure is far more profound and long-lasting than we thought.
the team is clearly optimistic that this is just the beginning. The methodology is sound, and the data will only get better.
Absolutely. The team suspects that future Gaia satellite observations, which continue to refine positional and proper motion data, coupled with continued spectroscopic analysis to reduce those velocity uncertainties we talked about, will continue to shed light on the exact origins of these ejections. And it will allow for more stars to be promoted to that reliable list.
So it's an ongoing effort.
It's an ongoing effort to solve what the source calls the deepest mystery in all of modern physics. It's an intellectual marathon, not a sprint.
This sounds like a monumental task, but the methodology using these reliable cosmic clocks as a basis for extreme velocity measurement is truly brilliant.
It is.
What's the final synthesis we should take away from this for the average learner?
I think the synthesis is this. This research beautifully demonstrates the power of astronomical methodology by leveraging a common, well-understood stellar type, the RR Lyrae stars, as a precise, standard ruler to lock down distance.
Right.
Astronomers can isolate these rare, extreme phenomena, the hypervelocity stars, and use them to probe the invisible, defining mass structure of our galaxy.
We're using the precise motions of visible matter to uncover the structure of invisible matter.
And that is a truly remarkable piece of indirect detection science.
That's a perfect encapsulation. We started with thousands of common pulsing stars and ended up with 87 confirmed cosmic speed demons,
All thanks to careful measurement and filtering.
insisting on that low uncertainty data. These hypervelocity stars are literally shooting out of our galaxy, and they're providing us with vital clues about the dark, invisible structures they're leaving behind.
The utility of these stars is profound. They transform the elusive theoretical gravitational potential of the Milky Way, which is the key to mapping dark matter distribution into something measurable and traceable. This work highlights how tracing stellar motion with extreme precision is one of our most effective and precise tools for revealing the mass distribution where dark matter hides.
And that leaves us with something critical to think about as we wrap up this deep dive.
Indeed. This research suggests two distinct populations of HVSs, one tracing back to the galactic center, and one potentially linked to the large and small Magellanic Clouds. So, if future research confirms that the Magellanic Clouds are indeed powerful enough to eject stars toward the Milky Way at such speeds, over 1,000 kilometers, what does that imply about the density and the total mass, and thus the dark matter content, of those two dwarf galaxies?
So if they are heavier than we think,
It changes our understanding of their gravitational influence, their own internal dynamics, and their ultimate fate as they orbit and interact with the Milky Way. That's a huge question with massive implications for galactic evolution, something for you to mull or explore on your own.